In section 3.2, we are going to learn some more properties of determinants. And in this first video, we are going to start by learning a theorem that makes computing determinants much easier. To illustrate the theorem, we're going to have this matrix A. It's a 2 by 2 with 1, 2, 3, 4 on the rows. And we're going to start by computing the determinant of A. And remember, the determinant of a 2 by 2 matrix is computed by multiplying the diagonal entries and then subtracting. So 1 times 4 minus 2 times 3 gives us minus 2 for the determinant of A. So A is going to help us illustrate this next theorem, like I mentioned. For the theorem, we're going to need an n by n matrix because we're going to be computing determinants, and we're also going to need a scalar c. Here's the first part of the theorem. If a new matrix B is obtained from the matrix A by multiplying a row or column of A by the scalar c, then the determinant of the new matrix B is C times the determinant of the original matrix A. So that's a lot to take in. Let's work through an example to see exactly how this works. So here's my new matrix, B. It has 1, 2 on the first row and minus 6, minus 8 on the second row. And the thing to keep in mind here is that this is just minus 2 times the second row of A. In case you forgot, our original matrix A is here, 1, 2, 3, 4. So let's check this property of the theorem by working through this determinant for B. So we multiply 1 and minus 8 and subtract the product of 2 and minus 6. So this is minus 8 plus 12, which comes out to 4. Now 4 is minus 2 times minus 2, so that's minus 2 times the determinant of A. And this is exactly what we expect to see from the theorem, since our matrix B has been obtained by multiplying the second row of A by minus 2. Let's move on to the second part of this theorem. If a new matrix B is obtained from our original matrix A by interchanging two rows or columns of the matrix A, then the determinant of B is the negative of the determinant of A. So what we're going to do now is swap the two rows of A to get a new matrix B. Now we have 3, 4, 1, 2 instead of 1, 2, 3, 4. And then we compute the determinant. We get 3 times 2 minus 4 times 1. So this is 6 minus 4, which comes out to positive 2. And this is the negative of negative 2, the determinant of A, just as the theorem claimed it should be. Now we'll move on to the third and final part of the theorem. If a new matrix B is obtained from the matrix A by adding a multiple of one row or column to another row or column, then nothing changes. The determinant of our new matrix B is the same as the determinant of A. So to illustrate this, I make a new matrix B by replacing the old second row of A with row 2 plus row 1 of A. just so we're keeping track. 1 plus 3 gives us the 4, and 2 plus 4 gives us the 6 in the second row. So now we compute the determinant. We need 1 times 6 minus 2 times 4. This comes out to 6 minus 8, which is minus 2. And that's the same as the determinant of A, what we started with. So we won't be going through the details of the proof of this theorem. If you want to see more details, you can check your textbook. It's a very technical theorem, and we're more interested in how to use it. So I said at the beginning that this theorem would help make computing determinants easier. Let's start with the 3 by 3 matrix. A is going to be 1, 2, 1, 2, 4, 1, 3, minus 1, 1 on the columns. My goal is to create more zeros in a row or column to make computing the determinant of A easier. Because we know that computing determinants of 3 by 3 matrices can take a lot of work. And if this was a 4 by 4 or a 5 by 5, that would be even more work. And we also know that if we have lots of zeros in a row or column, computing the determinant becomes easier. So to make more zeros in this matrix A, I'm going to take row 2 and subtract 2 times row 1. So the goal here is to create a 0 in this position. Here's what I get. I multiply by 2 and subtract, I get 0 here. I multiply by 2 and subtract, we get 4 minus 4, so that's another 0 on the second row. And then in the third entry of the second row, we have minus 1 minus 3 times 2, so we get minus 7 overall. So what we've done is created a new matrix by subtracting a multiple of one row from another. So going back to the theorem, part 3 of the theorem in particular, we know that when we do something like this, take a multiple of one row and add it or subtract it from another one, then nothing changes. The determinant stays the same. So when we compute the determinant of A, it's going to be the same as the determinant of B. Let's compute the determinant of B by expanding on the second row. So we have 0 times its corresponding cofactor. That won't contribute anything. We have another 0 times its cofactor. That'll also not contribute anything. So the only cofactor that matters is the cofactor from minus 7. So if you think back to our pattern matrix of pluses and minuses, we have a plus, minus, plus, minus, plus, minus. So this cofactor will have a negative sign. I put it out front. And then we have minus 7 times the matrix that we get when we delete the second row and third column. So what's left over is the 1, 2 on the first row and 1, 1 on the second row. So we get this new 2 by 2 determinant. And then we work through. Minus 7 is positive 7, and then the 2 by 2 determinant is 1 times 1 minus 2 times 1. So we get another minus 1 in here, and overall we get minus 7 for this determinant.